Thank you. All right. First of all, thanks everybody for coming after the dinner yesterday. I'll try not to disappoint, but if you need to rest your eyes for a minute, I won't take it personally. I know how it is. Yeah, so today I want to start introducing continuous background fields. And this is a familiar idea. It's something that you need to do before you can gauge. So I'll come to gauging in a little bit. But as I said, it's a familiar idea. Whenever you have a symmetry, with conserved current J, you can do the following modification to the action. You send the action to an action, the old action, plus I times the integral of J which B. And we call this object here the background field. So one of the topics of these lectures has been how to generalize this to the case that you don't have a well-defined notion of action and fields. So I will do that later. But whenever you do, this is one thing you can write. All right, so let's do a bit of dimensional counting first, situate ourselves. So for P-form symmetries, remember that our symmetry generator was the integral of J. So we can work out the degree of J from the dimension of the symmetry generator, and this was D minus P minus 1. Now, this was the thing that linked in D dimensions a P-dimensional object. So total dimension of the two things combined is D minus 1. And this implies, for this formula to make sense, if we are in D dimensions, that the degree of B is P plus 1. So a couple of familiar examples. Well, one familiar example, and then one unfamiliar example. If you take P equal to 0, then the degree of B is equal to what? To 1. In this case, we generate, instead of writing B, we write A. Of course, just a change of notation, but this will be the connection 1 form for the background field. So imagine that you are thinking of the quantum dynamics of a charged particle in a classical electromagnetic background. So your electromagnetic background will have some connection, A, and you're viewing it as the background for a global symmetry in which your charged particle moves. In actual electromagnetism, we do gauge A, so we're going to integrate over A, but we don't do that yet. First, we put the background, and then we sum over backgrounds. All right. In the case of Maxwell theory, the symmetry of interest had P equal to 1, in which case the degree of B is 2, And in this case, I will call it B. But we have two of those. Remember that the symmetry in Maxwell was an electric U1 and a magnetic U1, so we'll call the corresponding fields B and Bm in hopefully obvious notation. So Be is the thing that couples to electric current, star F, and Bm is the thing that couples to the magnetic current, F. Right. So let's do the electric background first. In some ways, this will be the most involved one, conceptually. So in this case, we take the current to be. There are some factors that I'm ignoring. They can go into the normalizations here. G equals J E to be I star F. So remember that there was a factor of I. When I constructed the generator of the charge, I did exponential of star F, so I put in the I here. So the usual formula with E to the I integral of J is still true. So this implies that if we turn on the background for the electric symmetry, we are sending the Maxwell Lagrangian, our action, to the Maxwell plus, okay. I put a minus to make formality prettier. No, actually plus is nice. Doesn't matter. Integral with a minus of J of B wedge star F. So what's this? We unpack things a bit. This is 1 over 2 E squared integral of F wedge star F minus integral of B wedge star F. And yeah. Okay. I'm going to be a little bit annoying and change conventions at this point. Sorry. I'm going to put an E squared here. And that's because I want to rewrite things in a nice way in a second. And the nice way is this one. 1 over 2 E squared F minus B wedge star F minus B. And then there's a term that I missed, which is, let's see, minus 1 over 2 E squared integral of B wedge star B. Okay. So hopefully I got the algebra right. The signs are not, so the factors are not super important. This is where I want to end up, so define B in such a way that this formula is the correct one at the end. Right. This last term, if you notice, is something that depends only on B. B is something I put by hand. It's not a dynamical field in the theory. So this is an example of what we call sometimes a counter term. Something you can always add to the theory. It's basically a number, right, that can go out of the path integral. So you're multiplying the partition function by some fixed number. We can always do this. And in particular, I can multiply the whole path integral by that term and get an action, now the effective action coupled to the background, which is going to be this one. Okay. So even if I started with the standard modification of the action, I'm going to take this as my real definition of coupling to an electric background, having this kind of action here. The difference between that definition and this one is that I have dropped this counter term that depends on non-dynamical fields. So it won't affect the dynamics, but it's easier and nicer to think in this way. Any questions so far? Yeah, that's right. So, exactly. So you have this coupling, which in this case is going to be B wedge star F up to constants. So the F goes here. This is, if you like, a fixed two form that I get to pick. That's my background. I define the path integral, the sum over oscillating fields, for this particular choice of background. Yeah, so there's no dynamical fields in there. I get to fix it as I want. It could be 0, it could be anything else I get to pick. Very good. Any other questions? Yeah.
Is the flat going to be, I mean, is its curvature 0?
I'm coming to that next. Yeah. And the answer is no. It doesn't have to be.
It doesn't have to be.
No, it doesn't have to be flat. No.
So could there be a problem with gauging variance if we remove the counter term?
We're coming to that. Yes. So yeah, I'm going to explain all that. If by the end of the lecture I haven't answered your question properly, you can ask again, but these are going to be my next few boards. Yeah. Any other questions? Okay. All right, so let's start answering that question. Assume B is flat. I'm going to drop the assumption in a minute, but let's go to a simpler case in which B is flat. And remember that flat means that dB is 0. Okay, so now this whole thing can be thought of as a connection on a bundle which is improperly quantized. So let's see this. Define what in string theory is often called curly F, which is nothing but straight F minus BE. The integral of curly F is the integral of F minus the integral of B. So this is valued in 2 pi integers plus some shift, which I'm going to call B. So in this definition, V is in R mod Z, and it's equal, modulo 1, to the integral of B, with a minus, yes, divided by 2 pi. Okay. So I'm really saying a triviality here. In general, we choose our F to be integrally quantized. There's no fundamental reason for this. Of course, this becomes very important once you have dynamical particles, dynamical electrons. But in pure Maxwell theory, that's a choice. One interpretation of this coupling is that we are altering this choice by choosing in each 2 cycles, so this depends on the 2 cycles, you say this. So this is an integral over 2 form over 2 cycle. So on each 2 cycle, I get to pick a shift of the quantization condition. In pure Maxwell theory, that's fine. Why wouldn't I do this? But of course, this has an effect in the theory. which is that now Wilson lines will feel the presence of this background field. That's a good thing. So recall, in P equal to 0, a background field introduces holonomies of point particles on one cycles. Okay, so what am I saying? You have a zero-form symmetry, like the example before. You had electromagnetism coupled to a dynamical particle, classical electromagnetism coupled to a dynamical particle. And you turn on a background for electromagnetism along the one cycle, you have introduced a holonomy for the particle. As you drag the particle around, it will pick up a phase. This is the Aharonov-Bohm effect. Yeah? You pick a charged particle, you move it along one cycle in a field, and it can pick up a phase. You're all familiar with this, I expect, right? Yeah. So we should expect to see something similar. This is the background of my symmetry. What are my charged particles for the one-form symmetry? I'm talking the electric one-form symmetry. So my charged particles are the Wilson lines. So I'm saying that as I drag a Wilson line on the proper notion of a cycle, a curve, it should pick up a phase. That's the generalization. Pick up phases as I drag them along. So which phase do you pick? Well, imagine that you have a, there. Imagine that your two cycle is a torus, just to make the picture simple. And you start with a Wilson line in here. With some charge q. So remember, this is the exponential of iq integral of a. And imagine that I take this Wilson line, and I do the analog of taking a charged particle and moving it around a circle. In this case, it will be taking the Wilson line and making my way around the torus and coming back where I was. Yep. So let's do that. I'm going to take my gamma, drag it along the torus, and end up in some gamma prime here. Which is on top of gamma, but after translating around the torus. So what's the change in the phase of the Wilson line? The integral of A on gamma prime minus the integral of A e gamma. Well, this is the gamma minus gamma prime, gamma prime minus gamma, is the boundary of this cylinder here. Let me call it C. So it's the integral over C of curly F, my electric field that now has some funny quantization. So one step of this argument, which is perhaps not entirely transparent, is why I chose curly F instead of straight F. And that's part of the definition of a background. If I want to do this non-perturbatively, as we'll see in a second, I'm not going to think out currents and integrations and so on. I'm going to think out insertions of defects. So this is the prescription that gives me really the action of the insertion of the defect in this case. Okay, this is the correct prescription, in other words. You choose the curly F, the thing that's gauge invariant. So differently, if you remember from our definition of Wilson lines, we took the Wilson line also to be possible to define by extending to a two surface as the integral of F with a Q. But once you couple to this background field, there's a gauge invariance in which you shift B and you shift F, as we did in the derivation of S-duality. So the gauge invariant object that I really need to couple to is curly F. This is the gauge invariant definition in the presence of backgrounds for Wilson lines. You can view them as the boundaries of these surfaces. So any of these two arguments tells you that this is the curly F in here. All right, so the integral of a straight F and the integral of B are these numbers here. This is going to be 2 pi n, because I'm going all around the torus. And this is going to be, in my conventions, 2 pi b. So this is equal to minus b mod 2 pi. In other words, the holonomy, or the action on the Wilson line, is that you go to the Wilson line times e to the minus see how I do this. Yeah. So there we go. Minus 2 pi I q b omega q in gamma. Okay. Any questions? Yeah. I don't need it to be flat. I'm assuming it's flat, and in a second I'll tell you what happens when it's not flat. I could have done this argument, as you say, for non-flat B. I will still pick a holonomy, but then I don't have the interpretation of curly F to be a connection on an improperly quantized bundle, because if it's a connection on a bundle, it has to be flat. That's why this interpretation depends on that. The fact that the Wilson line picks a holonomy does not depend on that fact. Yeah, very good. Yeah.
So could you please repeat why the integral, the difference of the intervals of A is equal to curly F, how that is consistent with those two?
Oh, yeah, sorry. Yeah. So maybe one thing. Okay, there's two questions there. One is, assuming A is the connection on the curly F bundle, this follows from Stokes' theorem in the following way, because gamma prime minus gamma is boundary of C. I can write this integral here as the integral over gamma prime minus gamma of A. And then Stokes literally gives me that.
So there we're assuming that curly F is equal to the A.
Yeah. So, sorry, that's what I was trying to justify here. I'm modifying my definition of the Wilson line to be the Wilson line with the connection on curly F. And the reason for that, one reason for that, if you want, is that if I define my Wilson line with curly F, which is the gauge invariant definition, then that's the right definition, right? That's, again, if you like, Stokes. Yeah, and a second reason for that will come in a second. That's probably the most obscure part of the argument, but it's good that you're asking questions. Any other questions? All right, so that's good. This background is really behaving as a holonomy, as a generator of holonomy, sorry, which is what background is supposed to do on charged particles. There's a second way of thinking about this, this phenomenon. Which is the following. This is something that's really only possible whenever you have a flat connection. So here I'm really going to use the assumption of flatness much more strongly. Okay. So second interpretation that is often useful, at least when thinking out formal stuff. Computationally, it's also useful if you're in low dimensions, which is the following. Recall something I mentioned a few times already in the course, that flat backgrounds, flat connections, if you want, are fixed by their holonomies. I'm talking about abelian and stuff always, so this is U1 statement. So how could I generate a holonomy for a charged object? Well, one thing I can do, so in P equal to 0, I could draw the following picture. Imagine that I select some curve in my space, and in a codimension 1 locus in this curve, I insert a symmetry generator. So a picture, in this case, the full picture, say that we are, for example, in D equal to 4, would be that we have the circle here and a 3 sphere in here. And we wrap the symmetry generator in the full S3 and a point in the S1. And now imagine that I take a charged particle, so some charged particle, and I drag it all around the S1, coming back to where it was. Then the charged particle will pick up a holonomy given by the action of the symmetry generator on that charged particle. You have to cross the symmetry generator, and that's precisely what symmetry generators do. They act with some group element on your charged object. On this one. Right. So hopefully that's clear. The same version of the argument we were doing for showing that symmetry generators generate the symmetries with some representation of the group. But in this case, the thing that I'm moving is the charged object instead of the symmetry generator through the charged object. But of course, the picture is the same. Okay, so this is a very simple toy example of the general philosophy that whenever you have a non-trivial bundle, this was just to draw something, but for non-trivial bundles, what you have is you divide your manifold into open sets, and you glue the different open sets with transition functions in the symmetry group. You have non-trivial bundle. Right? So there will be a generalization of that kind of picture. So for a generic bundle, you have something like this. You have open sets, then intersect. And in these places, you have some group elements, G1, G2, and G3, that tell you how to change from one patch to another. Yeah? So what this means in practice is that if you are dragging some operator along, and you want to see what happens to it in terms of holonomies, what you can do is introduce a symmetry defect here which is UG1, another one here, which is UG2, another one here, which is UG3. The action operators will be exactly the same. The holonomies will be the same by construction. But in practice, this is often a good way of thinking about what backgrounds are. So of course, this kind of picture generalizes very nicely. If you have higher bundles, this kind of picture is well, it's still true, but you have to be a little bit careful with the gauge transformations of the gauge transformations and so on. This kind of picture generalizes a bit more straightforwardly. All you have to do is to put the appropriate higher p-form symmetry generator here. So for example, for Maxwell, a B background, then a flat B background is a network so something like this, maybe, of UE, so that's exponential of some alpha star F, symmetry generators. So there'll be U alpha 1, U alpha 2, and so on. Okay. Of course, like in any bundle, there are consistency conditions. For example, if I cross all these, the transition functions have to loop consistently, and that amounts to the fact that these group generators have to fuse according to the group law. In this representation, this is very straightforward. If I call this U alpha 3, assuming the orientations are correct, this has to be U alpha 1 plus alpha 3, and so on. And that's very easy to read from this kind of expression. I have an abelian group. If I multiply these two U's, if I imagine these two ones not fusing suddenly, but kind of coming together slowly and then fuse them, then they have to add up in this abelian way. So charges have to be conserved. Right, does that want to say? Yeah, so there were a couple of questions about what happens when the background is not flat. So let's assume that dB is different from 0. I'm going to first try to justify what this means in this kind of picture, and then use an argument by duality to obtain the same conclusion. The pictorial argument will be a little bit heuristic. The other argument with duality, because I have proved duality, will be rigorous. But I think it's useful to see the pictorial argument first. So the claim is that locally, this corresponds to having networks with boundaries. So the picture is that I have a network. It's doing whatever it does around here, but at some point here it ends. So I have a UE. is here. You have a UE, and here it ends. Okay, and I would like to argue that this will induce a process that's effectively having curvature in the B background. Okay, so first of all, let's try to remember how can one of these symmetry generators end. That's something we saw in one of the previous lectures. Maybe easier to remember if we think of the magnetic generator first. Right, remember that this one was e to the I alpha integral of f. And basically by the Stokes theorem, we know that this can end on a particle with charge alpha. So massive particle, so that means equivalently a Wilson line with charge alpha. Right? So at some point we discussed, if you remember, that the quantization condition on the Q's for the Wilson line and on the N's for the Atoff lines came from the fact that we wanted to be independent of the extension. But we could define open operators. So this is a version of that kind of open operator. If I draw with more dimensions, the picture looks a bit like this, as I was drawing before. So you have the magnetic generator here and the Wilson line on its boundary. There's a similar picture if you dualize, in which you have an electric generator here, but then what you need to have here is an Atoff line of charge alpha. All right. So far, so good. Everybody with me so far? Okay, so I have said before that for a flat background, all I need to know is the holonomy. If you have a non-flat background, this means that as I deform the path, the holonomy can change. So I'm going to construct an example of a path that I will deform through the boundary, and the holonomy will change. And in that way, I will prove that there's a curvature. So let me study this path. We call this gamma. And the thing I want to drag along this path is a Wilson line. I want to compute the holonomy for the Wilson line. So let's say that there's a Wilson line that's wrapping a point in gamma times an S1 theta, and say that this one is not pictured. So there's an extra circle here going out of the board and wrapping the Wilson line on that. So it comes kind of like this, and I'm going to move it in this circle here. So the total space of this process is going to be a torus. So the total space of gamma times S1 theta is some torus. Okay. And let's look now at the change in the phase of the Wilson line as I drag it around this torus, as I just did back there. So the change in omega wrapped at some point in gamma times S1 theta is going to be as follows. omega at the point in gamma times S1 theta goes to omega point in gamma times S1 theta. So I end up in the place I started after I go around. But there's a phase, which is the exponential of e to, just a charge, sorry. So this is a Wilson line of charge cube. IQ integral on this torus of, let's say, gamma theta of f. Yeah, it's the same calculation I did before, only before I had the curly f. The reason I don't write curly f in there is because my network is localized. I want to claim that this process has B0 almost everywhere except at the location of the defect. So the integral is going to be just localized at the point. Okay. So this will be whatever it is, right? It depends, in this case, on what I have inside. So if I have exponential of IQ integral of f in this T2, well, I can compute it. Notice that in this case I have a monopole in there, and in the presence of monopoles, say heavy monopoles or out of lines, the integral of f on a two-cycle around the monopole is equal to 1. Just to say the monopole charge. And this is how you define monopoles. You take two surface that links the monopole, in whose interior you have the monopole, and if you integrate f around that, you get a fixed amount, a fixed number, which is the monopole charge that you have inside. Yeah.
Sorry, could you please repeat what they were using that instead of earlier? Because we're assuming that the
Yeah. Basically, I'm discretizing my picture and localizing all the holonomy at a discrete point there, and that line. So when I write integral of f in here, you should think of as the total flux in there, which you could interpret as the integral of curly f in there, if you like. Or I'm going to write a straight f, and then keep in mind that there's an intersection at some point with a symmetry generator. It's a bit of a singular configuration, so this is a little bit schematic. If I want to make it precise, I should smooth it a little bit and put curly f. But either way, there's some holonomy. The thing I'm after is in the change in the holonomy, not so much the holonomy itself. All right. So this was the definition of the top line, if you remember. I took my line, I constructed a two-cycle that linked it, and I have a fixed number in there that was the amount of monopole charge. Now, for fields that are quantized in the standard way, this is typically an integer. But in this kind of backgrounds, in which I introduce a B and my F is quantized in a funny way, have partial quantization, I can have fractional monopole charge. And in this particular in this particular case, that's alpha. Okay? When I write H alpha, that's the amount of monopole charge. So in this case, that's alpha. Okay, so that's my first calculation. And perhaps, sorry, just to keep conventions happy, should be 2 pi alpha and 2 pi I alpha. So the standard of lines will have alpha integer, but here I don't need to assume that because this is the end of an electric charge operator. It doesn't have to be properly quantized. Okay, so that's my first calculation. And it gives me a holonomy. This holonomy is invariant under deformations. Of gamma that don't cross H alpha. I can wiggle that dash line as much as I want. As long as the deformed line does not cross H alpha, I'm always going to get the same result in this calculation. The holonomy is always the same. So you see in this picture very manifestly, the statement I was making a few times that locally, that for a flat bundle, you only have information of the holonomies. That's the holonomies there. But the situation changes if I cross the endpoint of the electrical charge operator, that is the top line. So I have a picture like this, the same background. But now I'm dragging my Wilson line on some cycle gamma prime, which is outside this network. Well, in this case, clearly I'm not crossing any defect, so the phase of the Wilson line will stay invariant. So in this case, W Q of point gamma prime times S1 theta goes to itself. So you see that the introduction of the boundary, the fact that the defect ends somewhere, allows me to change the holonomy experienced by a charged object, by the Wilson line. And that's precisely the statement that the curvature of B is different from 0. The holonomies can change as I deform my lines. This is a discrete version of that. So basically, dBE is localized in this picture at the endpoints of UE networks. So boundaries, perhaps, boundaries of UE networks. So this is the lesson I want you to take out of this. But we can translate this into more concrete physics that has an interpretation in the continuum. As I mentioned, the boundaries of the UE networks, those are at-off lines. So those are massive insertions of monopoles. So from this calculation, I would expect that introducing a monopole density in my theory, putting a background of monopoles in the continuous formulation, will lead to having a non-flat dB. So let me try to show that. Any questions so far with that? Okay, so perhaps translating, I guess for the continuum, dB is something like a monopole current. All right, so let me try to show this in the magnetic case, and then because we know that electromagnetic duality exists for U1, for the Maxwell theory, I should be able to derive this statement at least in a dual frame. So let's do magnetic backgrounds. All right, so let's start in the same place we started with electric ones. I send S to S plus S Maxwell plus I integral of B magnetic, which J magnetic, and J magnetic is F. To have a B which F term in the action. And, sorry, conventions, 1 over 2 pi I, because I'm always taking the periods of, the F to be 2 pi I quantized, and the periods of B to be 2 pi I, B to be 2 pi periodic. So this makes the path integral well defined. All right. Oh. I don't know what that was. All right. This case is actually significantly easier to analyze, but I didn't want to mislead you with the easiness of this case because in general this picture is better. Thinking out junctions is something you can do non-perturbatively. Well, the technique I will use here is not generally applicable. But still, in this case, I can use it. So let me use it. Do integration by parts. This is what the Maxwell term. That doesn't change. And this one, if I do by parts, let's see, sign. This is the integral over dBm wedge A. I want to make a local statement, so I'm not being super careful about topology in here. Right? I'm thinking of a globally defined connection, a trivial bundle, if you want. So the equations of motion in this case are something like d star f, in other words, d of j electric equal to up to factors dBm. Now remember that in Maxwell's equations, whatever is on the right-hand side of d star f equal to something, that thing is a charge of electric density, a standard electric density, right? So electrons or something. So this implies that dBm different from 0 introduces electric charge. So here we went to do some contortions to argue the same statement for the dual case. I was arguing that the introduction of DBE amounts to introducing monopoles. Here in a couple of lines, I could prove that the introduction of DPM introduces electric charge, massive electric charge. But of course, to really relate the two things, I need to show that the electric magnetic backgrounds that I introduced are dual to each other. I sneakily call them BE and BM, but I haven't proven to you that those are really dual to each other. So let me do that next. So duality in the presence of which one again? Electric, yes. Magnetic. All right. So the goal here is proving that if I put a magnetic background in the electric description, I get an electric background in the magnetic description. So let me start with my duality manifest sort of Lagrangian. This was integral of f minus little b, which I'll define what these things are in a second. Sines plus plus. Okay. So B is the dynamical two-form field, previously known as B. So you check your notes from my derivation of the Maxwell duality. I was calling this big B, now it's called small b, not to confuse it with this, which is a background. There's a common convention in this field, which is that we call dynamical stuff with a little b when we need to distinguish. Stuff that's with lowercase letters, those are dynamical fields. Stuff that's with uppercase letters, those are fixed background fields. It's a convention. I'm not been following this convention religiously here, because if I did, I will have to put f in lowercase and ft in lowercase. So there's a bit of a mixed thing. But hopefully you are not confused here. So this one is dynamical, this one is dynamical, this one is fixed, and this one is dynamical. Okay. So first, let me prove that this is the insertion of a magnetic background in Maxwell theory. So doing the path integral over AD, say, I get that, as before, B is pure gauge. That doesn't change. I'm just talking about this term here. The fact that there's an extra term with a BM here doesn't change anything for that argument. The Lagrange multiplier, FD, will impose that B is pure gauge. And then I can gauge it away. I get the following: integral over 1 over 2e squared, f wedge star f, plus 1 over 2 pi I, integral of f wedge pm. And indeed, this is the magnetic coupling that I wrote up there. Right? Now let's go into the dual theory. So in this theory, you can view F as something that's always pure gauge, always has these kind of periods. So I can gauge it away. So gauging F away. I get 1 over 2 e squared, integral of little b, which star little b, minus 1 over 2 pi I, sorry, let me write it differently, plus ft minus bm integral wedge little b. And now, of course, I have, as before, I have a Gaussian in B. I can complete the square and integrate over B. And up to 1 loop factors, I get the dual description. Which is e squared over 2, integral of fd minus bm, which start of that. So indeed, what was a magnetic background in the original description has become an electric background in the dual description. Also, I know my dualities exchange F and star F. So my original slightly heuristic argument that B amounts to a monopole density has to be true. This is going to be sourced in df. Okay, any questions? Okay, so one exercise you can do is to run the argument starting from an electric background. That'll be a natural thing to do. And the final thing one would like to do is to put both backgrounds at once and run the argument. Now you run into a problem if you try to do this, so let me explain this problem. It will be our first example of an anomaly. So at a very basic level, what an anomaly is that if you turn some backgrounds for a symmetry, the symmetry is not conserved, some symmetry is not conserved anymore. So note that this all implies that dg electric is dBm magnetic. Well, sorry, I'm being slightly sloppy with constants today. If you want to fix them, you can. It's not very complicated, but it's not very important physically. So let me just write it like this. The important thing is that this is precisely a situation in which I have one of these non-conservations. If I turn on the background for the magnetic U1, then the current for the electric U1 is not conserved. Now, non-conservation of currents is closely related to non-gauge invariance for the background. So these concepts are very, very closely related, and the argument is the following. If you have a coupling which is integral of background times current, and you do a gauge transformation for the background, this becomes integral of background wedge current plus integral of T lambda wedge J, and by parts again, this becomes integral of B wedge J plus integral of lambda wedge dj. So you will get an extra term under the gauge transformation of the background if the corresponding current is not conserved. Now, there's nothing wrong with the theory doing this. I want to make this very clear. That's fine, and it's in fact very useful when you want to analyze theories. You want to see how they transform under gauge symmetries, and the transformation is very often not trivial. That's fine. This is an example of an anomaly in a global symmetry. Those are not inconsistencies. They are useful probes of the theory. But the thing that they imply is that you cannot gauge the theory which is anomalous. They're an obstruction to gauging. If you don't want to gauge, then you are not in any trouble. That's fine. So the technical term for such an anomaly in a global symmetry so meaning that the theory is not invariant under gauge transformations of backgrounds of the symmetry. These are known as Toft anomalies. You might have heard at some point the word global anomaly to describe these things. I don't like to use that word because it's also used for some specific type of anomalies for gauge symmetries that we'll see in a minute. So I find the terminology can get confusing, while a Toft anomaly is only used in this sense, so I'm going to stick to this convention. All right. So from these two equations together with this argument, I should be able to see, or I have proven basically, that there is a lack of gauge invariance on B magnetic, say, if I have a curved B electric. Yeah. So let me try to see that more explicitly. So the anomaly, once more, anomaly in Maxwell theory. So let me try to couple to both backgrounds without assuming that either of them is flat, and see that if I can see a bit more explicitly that this statement I found a little bit abstractly is true. Okay, so this is my action coupled to both electric and magnetic backgrounds. So this is 1 over 2e squared, F minus B electric, wedge star F minus B electric. There's the electric coupling. And then the magnetic coupling, 1 over 2 pi I integral of F minus B electric, wedge B magnetic. So here I come to the issue of counter terms. I have chosen my counter terms in a way that I can write the theory in this way. In particular, I have a term here which is B wedge Bm. That will imply, as I will prove in a second, that there is an anomaly in the gauge transformation of Bm, but not in the gauge transformation of Be. You can choose the counter terms differently to preserve the gauge transformations under Bm and break the ones in B. You can shuffle the anomaly around by choosing counter terms. The thing you cannot do is eliminate them completely. So here I have chosen counter terms in a way that I will preserve one of the two. Okay, so the gauge transformations are the following. Let's see. I send B to B plus D lambda E. As usual, I'm following physics notation here. You should view this as an integrally quantized two-form. Okay. If I do that, this term will not be gauge invariant, so I compensate that by sending A to A plus lambda E. And I'm going to keep Bm as it is. So this gauge transformation is, okay, the theory is gauge invariant under this transformation, no matter what the backgrounds are. So this is one, and that's okay. Let's do two, which is B and A, go to B and A. And then Bm goes to Bm plus the lambda M. So the theory is not anomalous. So the theory is not anomaly free. There is an anomaly that S goes to S plus 1 over 2 pi E integral of F minus BE, which the lambda M. So by parts, this is S going to S minus 1 to pi E, integral of the F minus B, which lambda M, and of course this is S plus 1 over 2 pi E, integral of dB, which lambda M. So we find indeed that this theory is not gauge invariant if the B background is curved. Any questions so far? Okay. So let's choose different sets of counter terms. Choose counter terms. Says that X Maxwell coupled to B and Bm is the kinetic term, integral of F minus BE, which F minus B plus 1 over 2 pi E, integral of F, which Bm. This would be another natural choice for the counter terms. Right? I'm dropping the BM counter term. In this case, you see that this transformation is okay. It's gauge invariant. So under 2, you get that S goes to S plus 1 over 2 pi I, integral of f wedge t lambda m. And integrating by parts, this term vanishes because f is flat. But, of course, you have a problem if you do this transformation here. The kinetic term stays gauge invariant under this transformation. I chose the counter term, so at least I could have that. But this term here, because f shifts by d lambda e, will shift. So under 2, so under 1, S of BBM goes to S BBM plus, and a shift coming from this term, the variation of f. So that's 1 over 2 pi I, d lambda e, which pm, and of course, this is equal to S BBM plus 1 over 2 pi I. Okay. So again, if you turn on a non-flat background for BM, you have an anomaly in the electric transformation. So you can always play this game of shuffling the anomaly around by counter terms, but you cannot eliminate it. Yeah.
What are the secret control counter terms? Starting with the, let's say,
If I don't drop the... Well, you have a choice of counter terms. There's more choices I could have taken here. For example, there was one that was B wedge star B. Is that the one you're talking about?
Well, we started with by adding when we added the ground, we added as a variable, so is B wedge star F.
Yeah, exactly. So the difference between that background being inserted and this term is B wedge star B. So you have the F wedge star F that you always have. You have the coupling to a current, which is F wedge star F wedge B, E. And then you have B wedge star B. So the difference between what we wrote originally and this one is that counter term. And well, that term is basically the square of a connection. So it's going to give us trouble. You can try to show by yourself that there's no real gauge invariance that you can do to save it in any particular way. So writing things in this way allows me to salvage some gauge invariance by shifting F also. Yeah, I'm just... it's valid, it's a question, which is perfectly valid. You can go through analysis and you will see that there's no gauge invariance you can define that generalizes these two, that makes that term with the rest of the Lagrangian or the action gauge invariant. Yeah, thank you. Any other questions? Yeah.
Magnetic and our electric only with the flat bundle. This is not kind of related.
That's not what?
It's not really related because we cannot reintegrate the part.
Yeah. I'm being a little bit sloppy with differential forms and so on. Yeah, you're completely right. Okay. Yeah. Yeah. In this case, the analysis is almost classical, as you say. And you will see that the effective action if you just exponentiate this, it won't be gauge invariant because the action itself is not gauge invariant. So these things here, they don't have integral periods in general. So putting an exponential in front won't save you. Yeah. Any other questions? Yeah. Yeah, thank you. That's a great question. This is an abuse of language that's very often made, and I just made it, and it can be confusing, I agree. These are classical backgrounds. I have no reason for expecting that this has to hold. So this is the point I was trying to make before. A Toft anomaly is nothing sick with the theory. The fact that the theory is not invariant under this transformation, it's in some sense almost a virtue. It tells us information about the theory. If I were to try to gauge this, meaning summing over backgrounds, then this would be a real problem because when you do the path integral, you want to have gauge invariant, otherwise the sum tends to get 0. Yeah. Yeah, very good. Any other questions?
Maybe it's out of context, but I've always seen the anomaly as a non-invariant of effective quantum action. It was an invariant of the classical action.
Yeah, you're right.
On a classical determinative theorem. And I'm not getting why we are using the...
Well, I'm using the word anomaly. Yeah, yeah.
Can we see it as simply as a non-symmetry of the action? It's not a symmetry of the classical action. Why should we?
Yeah, in this particular case, that distinction is not, you're completely right, yeah. In this case, that distinction is not particularly manifest, the way I presented things. But notice that I'm talking about the magnetic and electric symmetries at the same time. The concept of monopoles and these non-trivial bundles is, to me, more of a quantum property of the theory, something that appears when you have a quantum theory, because I'm talking about non-trivial bundles with A. So it is in that sense that I use the word anomaly. I get the point of your question. All my analysis was in the terms of the action. I didn't ever compute a one-loop determinant or anything like that. So if you're unhappy with calling this an anomaly, because of that, I'm okay. But this is a true fact, that this is not gauge invariant. Now, with the modern definition of anomaly, which I will present in a second, this is much more clearly an anomaly. Okay. So with the old definition, I agree with you. It's not entirely obvious why this should be called. In the old definition, in some sense, anomaly was synonym with surprise. You had some classical symmetry, you quantized it, and it broke. I will make the claim that perhaps these symmetries are not very classical to start with. So how much of this surprise is, I don't know. We have now a modern definition of anomaly, which I'll introduce in a minute, and then this is clearly an anomaly in that sense. Yeah, very good. Any other questions? Right, so let me sort of introduce, and I'll go in much more detail in coming lectures, the more modern version of anomalies. What do we mean by an anomaly? So I'm going to fix the lack of gauge invariance. By coupling to a 5D bulk. All right. So the exact anomaly, the exact failure of gauge invariance in this case, depended a bit on the choice of counter terms. So let me make a precise choice of counter terms just to get a definite analysis. So choose counter terms. such that my Maxwell action is this one. Okay. So let me choose this case, and if you remember in this case, the thing that failed was the gauge transformation of BM. So under BM goes to BM plus d lambda m. X Maxwell goes to X Maxwell plus minus, I think. Plus. Right? So that's a fact of life. What I'm going to do is to modify my theory. I'm going to construct a new theory. By coupling to a 5D bulk. So choose some M5 such that the boundary of M5 is N4. And we write the following: is Maxwell prime, say, probably have a better name. Yeah, Maxwell prime. This is S Maxwell plus S5D with S5D to be 1 over 2 pi I integral of dBE, which, sorry, how did I choose the conductors? Yeah, BM, which dB. All right, so that's an action for a 5-dimensional theory. I want to emphasize that this is a very, very boring 5-dimensional theory, right? So here, BM and B are non-dynamical extensions to 5D. So you take your fields on the boundary, and you extend them in some way. You get to choose how you extend them to M5, and then you write an action for those. But you don't sum over extensions or anything like that. You pick one extension and you stick with it. So if you want the partition function of the 5D theory, depends on the backgrounds, BM and B, or these extensions of the backgrounds. Let me put 5D here to make that clear. And then it's just e to the minus s 5D for these backgrounds. Sorry for the mess. But hopefully this is clear. The point I'm making here is that there is no path integral. The partition function is simply the evaluation of the exponential. Yeah. So this is a theory with no dynamical fields, but it depends on some background fields, and it depends on the background fields in this way. It's a theory of purely counter terms, if you want. So advancing a little bit, something I will spend more time doing in coming lectures. Advancing something I will spend more time doing in coming lectures. This is an example of an anomaly theory. Okay. Any questions about the definition of this object? Very good. Now, clearly, under a Gates transformation, of the 5D fields, restricting to those Gates transformations above. What do I get? That S5D goes to S5D plus, well, BE, because I have a D here, that term will be invariant under 1. So the only Gates transformation that gives me something interesting is 2. So let's write it. This is 1 over 2 pi I integral of d lambda m, which dB. So I can write this, and this is over M5. I can write this as S5D plus 1 over 2 pi I, use Stokes, integral over the boundary of M5 of lambda m, which dB. And that variation of the 5D action exactly cancels the variation of the Maxwell action. Remember that these two things are odd degrees, so they get a minus sign when you change the order. So S Maxwell prime is Gates invariant under 1 and 2. Of course, there's a cost to pay, there's a price to pay. How do we do it? There's a price to pay, which is that I made some choices here. The choice of M5 and the choice of extension. So I have potentially, instead of fixing a 4D theory, I have defined a 5D theory with better behavior. So is Maxwell prime, perhaps with the yes. This new theory is a 5D theory. And one test for this being a 5D theory is that the partition function of this theory depends on the extension. If I can prove that the partition depends on the extension, then I cannot forget about the extension. Really, I have to define things in 5 dimensions. I no longer have purely 4-dimensional theory. Remember, going back to our first lecture, my definition of quantum field theory was something that, given a manifold in d dimensions, gives you a partition function. I no longer have that in 4 dimensions. I have something that, given a manifold in 5 dimensions, gives me a partition function. So let's do that. Let's compute the partition function of Maxwell, sorry, no, first choose M and M prime such that, so the standard argument really, boundary of M is equal to boundary of M prime equal to N. So the picture is that I have my Maxwell theory defining some M, N here, and I pick two extensions. These extensions can be quite different topologically, but even if you pick the same extension, you still have to pick the extensions of the background fields. So I'm not going to put that in the notation, but you have to tell me how you pick these 5-dimensional BM 5D and BE 5D. And these two choices can be different. Even if these two geometries, you choose them to be the same, which you can, you still have to choose this, and you can choose this differently for the two extensions. Right. So now I'm going to glue in M with the change of orientation and M prime along N. I have a picture that looks like this. So this is M, and this is M prime. I have a picture that looks like this. And this is a manifold set. Sorry, set a separate name. This is a manifold P, say, and P has no boundary. All right. So let's compute set Maxwell prime with the choice of extension M prime and some choices of B and BM divided by set Maxwell with some other choice of extension M in B, BM. Again, this should be extended, so let me write this 5D. Okay, so the partition function of the theory on the boundary, the part where I'm gluing, is always the same. I always have the same Maxwell theory. So the only thing that gives me a non-trivial contribution here is the 5D action. So this is going to be e to the minus s 5D in M prime, B, BM, everything 5D. Okay, so what's that? Well, these are just integrals of B and BM and BE with a D. Right? So when I write the integral explicitly, what do I have? Exponential of minus 1 over 2 pi I. Okay, let's see. Integral over M prime of B 5D, which D BM 5D, minus integral over M from here, B 5D, which D BM 5D. And of course, that's just the exponential of some phase, 1 over 2 pi, integral over p, assuming I choose my conventions reasonably, yeah, of b5d, which d bm 5d. And generically, this is different from 1. So to see this a little bit more clearly, let me go yet one dimension higher. So choose some q such that the boundary of q, so some q such that boundary of q is p. And then the thing I computed there, this factor here, let me give it a name, e to the phi, e to the phi by Stokes is the exponential of -1 over 2 pi I integral of dBE 5d, which dBm 5d. Now, at this point, there's something very tempting to say, which is wrong, which is that because these things are 2 pi quantized, you get the 2 pi from here, 2 pi n, 2 pi m, so this whole thing is exponential of 2 pi n times I, so it's 1. That's not correct, because the picture is a bit like this. You have a P, you have a Q, and the statement is that these fields are integrally quantized when written in manifolds without boundary. That is, if I were to extend Q to some extra factor here, Q prime, then the integral of these fields over the whole thing will be indeed 1, because I'm chopping off a piece. This integral is arbitrary, depends on the curvature. So just to give you something that's a bit easier to picture, if you have a 2-sphere and you put some U1 bundle with curvature that you localize around this half, the total integral of the curvature will be 1, whatever it is, but depending where you do the integral, you pick more or less of this curvature. Okay? So this integral is not 1, therefore that integral is not 1, therefore this thing depends on the extension. So this is our first example of an anomaly theory, and we'll see much more of this in coming lectures. Okay, thanks.